Thank you for giving me a chance to talk in this place. I'm purely differential geometry, so I'm not good at information geometry or about GSI components. So I'm pleased to give me this place. I try to interest the real hypersurface in complex quadratic with certain condition of normal Jacobi operator. The normal Jacobi operator is given by Riemannian curvature tensor in complex quadratic, and so the definition of a complex quadratic is this is the set of all homogeneous coordinate in complex projective space Cpm plus 1, satisfying these algebraic equations like this one, where from Z0 to Zn plus 1 it describes the complex numbers in complex Euclidean space, and this naturally this gives complex hypersurface in complex projective space, and this gives Riemannian manifold structures that especially complex quadratic QM gives complex hypersurface in complex projective space. That is the complex codimension has 1, and this gives Riemannian manifold, and this has a Riemannian metric G and Riemannian connection blah. And the special orthogonal groups act on complex quadratic QM, and K is isotopic subgroup of G, and where this is a special orthogonal group, and K is consists of dual matrices of special orthogonal groups like this one, and naturally QM gives diffeomorphism to G over K. This is considered as topological spaces. It is quotient space, and by the computation of dimension of G over K, then this gives 2n dimension, real 2n dimension like this one. And I'd like to show the shape operator of QM in complex projective space AZ bar, and AZ bar gives complex conjugation on the tangent space of complex quadratic, and this gives anti-commuting involution on this space, and lambda is the set element of a complex number where S1 is one-dimensional sphere, and this lambda z bar is express all normal vector field on complex quadratic in complex projective space, and since this gives involution structure, then we can decompose the tangent space of complex quadratic by VA and JVA, where JVA means that the plus one eigenspace of complex TZQM, and this gives minus one eigenspaces. So this is important in the description of complex tangent space of complex quadratic, and the Riemannian curvature of complex quadratic in complex projective space gives by the second of the Gauss equation. Then since QM has two normal vector field in complex projective space, these two terms appear respectively, and whereby this is a Riemannian curvature tensor of QM, where J is the Kähler structure on complex quadratic, and A is the shape operator when I before mentioned before. And from now on, I'd like to introduce real hypersurface in complex quadratic. Complex quadratic is complex hypersurface in complex projective space. So they have two normal vector field, and M is real hypersurface in complex quadric. There is only one normal vector field on. There exists on only one normal vector field. From now on, let n be a local unit normal vector field on M. And naturally, we can consider the shape operator of M, S by S, and Riemannian metric and Riemannian connection like this one. And from the Kähler structure on QM induces almost contact matrix structure like this one, where G is Riemannian metric and J is Kähler structure. Since we can decompose the Jx by pi x and eta x, where pi is tangential component of Jx and eta x is normal component of Jx, where Jx is tangent vector field on M, and this four pairs has this property like this one, and I'd like to introduce one tangent vector field, cosine. It is defined by minus Jn, where we recall that J is a Kähler structure and N is a unit normal vector field. And this describes the tangent vector field on that we call cosine is a Lie vector field on M. This describes the tangent vector field on M. And when we consider the CPOP by Lie vector field cosine, and we can decompose this is orthogonal complement of CPOP. And we can decompose the real hypersurface on M. And I'd like to introduce a singular tangent vector field on QM. In the symmetry space, in complex quadric is rank 2 symmetry space. In given tangent vector on QM, there exists at least one singular, at least one more maximal flats in complex quadric. There is the definition of W is singular. There is in given W there exists more than one maximal place in complex quadric. This is definition of a single vector field. And in complex quadric, there is two types of complex. There is maximal place. W is singular. If there exists complex conjugation A, that is such that W belongs to +1 eigenspace of shape operator A, then W is a singular vector field. In this case, I will call such a single vector field by R principle. And the second one, if there exists complex conjugation and two pairs of orthogonal basis such that the unit norm of W is expressed by this vector field equation, then we call by R isotropy. So it's in the complex single vector field, and this arbitrary tangent vector field W is given by these two linear combination. And in this case, a singular tangent vector field on QM is expressed by T equal to 0 or T equal to pi over 4. First case, T equal to 0 is R principal vector tangent vector field, single vector field, and the second one is correspond to R isotropic tangent vector field. When T equal to 0, then W equal to X, and this there exists many kind of flats, and also we see that T equal to pi over 4. Also, there exists more than one tangent vector field, and if t equal to t is more than 0 and less than 5 or 4, then there exists only one maximal plane in complex quadric. And let them be a unit normal vector field in complex quadric, and we can choose shape operator A such that normal vector field n equal to this one. And this is a property on complex quadric, and where Z1 and Z2 is a plus one eigenspace of A. And we can by computation of an and psi is comes from the expression of a unit normal vector field, where since A is act on complex tangential vector field on complex quadric, and psi is defined by minus Jn and so on. And I'd like to introduce classification theorem on using the n is singular vector field. First, n is isotropic normal vector field, then m is locally congruent to tube over totally geodesic CPK in complex quadric. And the second one, if n is R principal, then a contact type of surface M is locally congruent to tube over M-dimensional sphere. This is a reference to papers. I'd like to introduce the Kodachi equation. Kodachi equations comes from the Riemannian normal component of Riemannian curvature tensor on complex quadric QM. This is describes the normal part of Riemannian curvature tensor. In this case, we see that the left side is given by shape operator of M by this one. This from this equation, I consider the normal Jacobi operator of Kodachi type, and I will show that if the Ricci tensor, let them be a Ricci tensor on M, then the Ricci tensor satisfying this equation, then M has a harmonic curvature. This we call by this one. And if the Rm bar be a normal Jacobi operator of real hypersurface M, then if this is satisfying this equation, then the normal Jacobi operator of Rm bar is said to be Kodachi type. But from the exterior derivative, then arbitrary p form omega is has satisfying this equation by using the exterior derivative. And when you consider the Rm bar is one type tensor field, and you can compute it by this one equal to this one. So the normal Jacobi operator of Kodachi type is equivalent to this is exterior derivative of Rm bar equal to 0. This is description of exterior derivative. I'd like to explanation of previous result, and let it be a whole hypersurface with harmonic curvature. Then the principal curvature has 5 like this one, and the principal space is like this one, and those principal curvatures satisfying these algebraic equations he found, and is isotropic normal vector field. Then also they have at most 6 distinct principal curvature like this one, and principal curvature space is given by this equation. I consider the problem of M is Hopf hypersurface. The Hopf hypersurface is Lie vector field. Psi is principal vector field on M, on all of point of M. That is equivalent to the fact that integral cover over Lipp vector field psi is geodesic. Then second condition is my main condition. Rn bar is of Kodachi type. Then what type M is locally congruent to. This is my main question. And I found the lemma, let M be a Hopf surface in complex quadric with normal Jacobi operator of Kodachi type. Then Lipp normal vector field must be singular. That is, N is either to isotropic or R principal. And using this lemma, we can divide the two conditions. First one is R isotropic, and the second one is R principal. On each cases, I have a result respectively. In this case, there does not exist on each singular vector field cases with this equation, these conditions. So my presentation is all of this one. Thank you for your attention.
I thank all the speakers, and enjoy the rest of the conference.